Maths in Action, a beautifully compelling tribute to mathematics. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. Since it was considered that it did not convey the spirit of Maths in Action, I have decided to call it Maths in Action. So the question is, starting with just a straight line, just what and how much mathematics can we generate? So let's see. Draw a line. Replicate the line, set it at right angles in the centre of the first line. Replicate the line, set it at right angles in the centre of the second line. Replicate the line, set it at right angles in the centre of the third line. Join the four vertices to form a square. Draw a square so as to touch the four vertices and with its sides parallel to the internal square. How many distinct diagrams can you see in just this one diagram? Diagram 1. We have a square of dimensions a plus b all squared containing a square c squared plus 4 right-angled triangles with sides a and b and area a times b over 2. Therefore, a plus b all squared is equal to c squared plus 4ab all over 2 is equal to c squared plus 2ab. Therefore, a squared plus b squared plus 2ab is equal to c squared plus 2ab, which on cancelling the 2ab on both sides leaves c squared equals a squared plus b squared, QED. Diagram 2. We have an internal square of dimensions a minus b all squared plus 4 right-angled triangles with sides a and b and area a times b all divided by 2 within an outer square c squared. Therefore, a minus b all squared plus 4ab all over 2 is equal to a minus b all squared plus 2ab equals c squared. Therefore, a squared plus b squared minus 2ab plus 2ab equals c squared, which on cancelling the 2ab's leaves a squared plus b squared equals c squared, QED. Diagram 3. We have a square of dimensions a plus b all squared consisting of an internal square of dimension a minus b all squared plus 4 rectangles of size a times b. Therefore, a plus b all squared is equal to a minus b all squared plus 4ab. This is more commonly stated as a plus b all over 2 all squared minus a minus b all over 2 all squared is equal to ab, and called the quarter squares rule. The quarter squares rule is actually proposition 8 of book 2 of Euclid's Elements and was described as being of little importance in Hall and Stevens' 1889 edition of Euclid's Elements. We have just shown that it is far from being of no importance. Returning to where we were on slide 5, we can rotate the internal square equal to 1 squared until its sides are parallel to those of the outer square. Labelling the large side of the rectangle A and smaller side B so that the outer square is now a plus b all squared and inner square a minus b all squared, we get the equation a plus b all squared minus a minus b all squared equals 4ab, and so again we have constructed the quarter squares rule. So can we deduce anything special about the rectangle we have produced? Well, knowing a plus b equals root 5 and a minus b equals 1, then a plus b minus a minus b equals 2b. Therefore b equals root 5 minus 1 all divided by 2 is equal to 0.618033988, and A equals 1 plus B, the golden ratio, 1.618033988. Apart from having constructed the irrational incommensurable quantities root 5, the golden ratio, 1.618033988, and its conjugate, 0.618033988, we have as a bonus root 2, the diagonal of the unit square, and as a consequence the hypotenuse of a right-angled equilateral triangle, of side equal to 1, about the right angle. Now that's maths, that's mathemagic. Just to embellish what we have just found, in Euclid's Elements, a book on geometry written circa 300 BC and which paved the way for present-day mathematics, we find definition 4 of book 6, which states, a straight line is said to be divided in extreme and mean ratio when the whole is to the greater segment as the greater segment is to the less. Hence 1. PR divided by PQ is equal to PQ divided by QR by definition. Let PQ equals 1, then 2. PR divided by 1 is equal to 1 divided by QR, and 3. PR times QR equals 1. 4. 1 plus QR times QR equals 1. Therefore QR squared plus QR minus 1 equals 0, a quadratic equation. From the diagram, A plus B equals A minus B plus 2B. Therefore B is equal to A plus B minus A minus B all divided by 2. When A plus B equals root 5 and A minus B equals 1, therefore B equals root 5 minus 1 all divided by 2 is equal to 0.61803398875, and A equals 1 plus B, therefore AB equals 1.6180339 times 0.6180339 equals 1, as the numbers and equality 4 predicts. The golden ratio and its conjugate are the only two numbers that satisfy definition 4 of book 6 of Euclid's Elements. The golden ratio is the progenitor of two series of identities that have the same form and comparable mathematical behaviour as the golden ratio. The first is given by a squared minus 2 squared, where we continually increment a by 1 to give the following table. We then proceed as per the golden ratio to give root 12 plus or minus 2 all divided by 2 equals 2.732050808 and 0.732050808. Root 21 plus or minus 3 all divided by 2 is equal to 3.791287847 and 0.791287847. The first set of golden ratio identities, which after multiplying the two terms together gives the integer part of the larger term as the product, as shown in the bottom of the two tables. A hidden yet nice consequence of the first set of golden ratio identities is that if we take the binomial partition of the integer and apply it to the integer part of the terms, leaving the decimal as is, then on multiplying out we still get an integer result, as the following example for 7 demonstrates. The first set of golden ratio identities is an inherent property of the integers, as the following slide shows. The table shows the quadratic equations associated with the first and second set of golden ratio identities. The second set of golden ratio identities are the roots of the second set of quadratic equations and obtained via the recursion equations A equals A reciprocal plus B, or A plus B all reciprocal, where the output is continually fed back into the equation, starting with a seed value until a constant decimal expansion is obtained. The product of the two roots of the second set of the golden ratio are all equal to 1. The slide shows the display on the calculator after carrying out the recursive equations. The second set of golden ratio identities are commonly known as the metal series, because we have the golden ratio, the silver ratio, and in this case my terminology, the brass ratio, although it is often called the bronze ratio. In a number file video, Matt Parker demonstrated that both the odd and even powers of the golden ratio, when rounded up or down to the nearest integer, gave the Lucas sequence. What he failed to spot was that the values of the odd powers gave rise to some of the metal series, as shown in the table below. So yet again, that's maths, that's mathemagic. The even powers also display their own characteristic. 1. When multiplied by the decimal part, the number decreases by 1. 2. Multiplying the reduced number by its decimal part gives the integer part of the number. The integer plus 2 gives a Lucas number. It is quite interesting to change the B and C coefficients of the quadratic equations and determine their roots. You will find the golden ratio trend continues. I don't know what you have got from what I have shown, but what I take from it is this. 1. The integers are a perfect number field, and questions such as what number will be the next prime, or are there an infinite number of twin primes, whilst legitimate to ask, have, as far as I can see, no bearing on that perfection or the basic fundamentals of number theory. 2. Likewise, the real numbers, whilst to some are seen as behaving irrationally, simply because they are perplexed by their infinite nature, do in fact behave in a very rational and predictable manner, which is only to be expected, since they are, after all, intimately linked to the integers. 3. I find algebra, numbers and geometry perfect tools for investigating basic number theory, and work well either on their own or in partnership with each other, and the over-egged demand for so-called rigour and proof to infinity are for the most part just ploys of the intellectual elitists, i.e. Fermat's 4n plus 1 prime conjecture. Algebra, quadratic equations and proof by example are all any rational-minded person's needs. I hope you have enjoyed the maths, and thank you for watching.